Hi everyone, this is going to be a video walkthrough for problem 4A on C61BL Summer 2021, the final. So let's get started by reading the prompt because I think this question in particular is a lot to digest. I'm going to skip this backstory and just dive in right here. So the problem states, suppose we want to sort n distinct strings, each of length w, that are comprised of characters from an alien alphabet of size n squared. So this is definitely a lot to take in. Let's first try to look at this image to try to understand it, and then I'll give you guys an example in the English alphabet. Okay, so looking at this visual, what we'll notice is that these are our n strings that we need to sort, right? We have 1, 2, 3, all the way up till n total strings. Each string is length w. So this length w is a bit different than what we've seen in a lot of sorting algorithms up to this point, because usually when we run merge sort or any comparison sorting algorithm, we don't really consider the time it takes to compare two things. But now that the length is w here, we'll see that that kind of factors in, right? And another thing to kind of take away here is that each character comes from an alphabet of size n squared, right? So that's like also a little strange. And I think if this visual is still a bit confusing, we'll try to revisit this when we look at merge sort. And I want to get started by first reading this and then tackling merge sort. So the problem asks, what are the runtimes of the following sorting algorithms in the best and worst case? If we use some sorting algorithm, say quicksort as the subroutine in LSD or MST sort, that means we use quicksort to sort each character, exactly how counting sort is traditionally used as a subroutine. If two strings are distinct, that means at least one character differs. Finally, if the sorting algorithm provided would not work, use select would not work. And our answers may involve both W and N. And a helpful hint is that when we compare two strings, it takes constant time in the best case and W time in the worst case. So the reason why this hint is true is, let's say that we have bear, beat, and fear. Notice that if I'm comparing the strings starting from the first character, in order to realize that bear and beat differ, I have to go all the way to the end, right? So if I ever compare bear and beat, this takes me W time. On the other hand, if I compare fear and beat, notice that right as I look at the first character, I realize they're different. So this takes me constant time. Okay, so that's just kind of the reasoning for the hint there. Now let's look at merge sort, right? And when we're looking at merge sort, what I want to kind of touch upon is that we don't really care about this idea. The alphabet size really only comes in when we think about radix sort, okay? Because if the alphabet size is like 1,000,000, it's not going to change anything about how long it takes to compare two strings, right? When we're running merge sort, we only really care about this hint, right? How long it takes to compare two strings, which isn't dependent on the alphabet size. So let's consider the best and worst case here. So first, what is the runtime of merge sort? The runtime of merge sort, as we've learned in this class, is n log n in the best and worst case. Right? So I'm not going to get into the details of why it's n log n, but what I want to say is that the runtime is n log n, and we also perform n log n comparisons in the best and worst case. Okay? So the reason we perform n log n comparisons in the best and worst case is that every time we do a merge operation, right? So let's say I'm merging 1, 2, 7, 8 with 4, 5, 9, 10. Notice that at every step in this in merge sort, we're basically doing a comparison, right? So in that light, what we'll notice is that the runtime of merge sort of n log n just comes from every step in the algorithm, and every step of the algorithm is basically just acting upon a comparison, okay? So In merge sort, we have n log n comparisons, and we know a comparison takes constant time in the best case and w time in the worst case. So what we can say is that our best case is going to be n log n because every comparison takes constant time, right? So our best case is going to be n log n. And then in our worst case, every comparison takes w time, and our worst case is w n log n, right? Okay. So moving on to the next part, now we're running insertion sort. So in a similar light, when we're running insertion sort, our best case is n, and our worst case is n squared, right? And in our best case of n, it's because we do n comparisons, right? To kind of show you all an example of this, notice that if the list is in sorted order, when I am at 2, I compare 2 and 1, right? That's one comparison. When I'm at 3, I compare 3 and 2. It's another comparison. When I'm at 4, I compare 4 and 3, another. 5 and 4, that's another comparison. So we can see that the best case of n in insertion sort is because we are doing n comparisons, right? And then the worst case of n squared is because we're also doing n squared comparisons. In the worst case behavior, it's when the list is sorted in reverse order. And every time that we're at some element, let's say we're at 2, we have to keep comparing it to every element before it, right? So what I'm trying to say is that the best case in terms of comparisons is n and n squared, or best case is n, worst case is n squared. So if I'm looking at the best and worst case runtime, the best case is that we do n comparisons, and each comparison is constant time. Right? The worst case is that we do n squared comparisons, and each comparison is w time. So what we can see is that the best case is going to be wn, and the worst case is going to be wn squared. Or that's not wn squared. This is wn squared. Okay. So now we're entering the idea where the alphabet size of n squared kind of matters. And what we're going to be doing here is we're going to be running LSD sort with counting sort as the subroutine. Recall that LSD sort conventionally uses counting sort as the subroutine. And when we run counting sort, what we're going to do is translate each character into a number between 1 and n squared. So I think this is like maybe a bit confusing what's happening here. So let's think about this in terms of us with some strings. Okay, so let's say that we have 5 strings. Let's say help and meet with rats. Okay, so what I want to kind of notice here is that n, or the number of strings we have, is 5, right? Each string is of length 4. And if we're looking at the alphabet size, right, is 26 because we're using like the English alphabet, right? And this is basically the same as the problem that's given. We have some n, we have some w, and the alphabet size in the alien alphabet is n squared, which is basically 26 in our example. So I think this list of words is very representative of the problem we're trying to solve, so it may help us to gain some intuition for what to do. Okay, so if I'm running LSD sort with counting sort as a subroutine, what we're going to do in the first pass is we're going to look at, quickly copy this. Yeah, so just looking at the first pass of LSD radic sort, we're going to look at all of these digits, or these last characters, right? So when we run LSD radic sort, what we want to do is sort all of these strings on these characters using counting sort. So counting sort requires that the elements that we're running counting sort on need to be between like 0 and some upper bound, right? Usually in most things we see in this class, we usually run LSD sort on some strings, right? In which case, when we run counting sort, what we do is we usually run LSD sort on some numbers, and when we run counting sort, we compare the last digits, right? So counting sort is easier for us to do when these last digits are numbers, but it's not too hard. What we can do is that we can translate each one of these letters to a number, okay? So I think A is the first letter of the alphabet. I think T is 20, but don't quote me on that. So that means S is 19, H is 8 maybe, and then P is, I'm just guessing 16. 17 is my guess. Okay, this is probably wrong, sorry. But anyways, so what we've done so far is we've taken each one of these letters and we've converted it to a number. Now with these numbers, we're going to run counting sort, okay, on these numbers. And that's one pass of LSD radix sort. And we're going to do W passes, okay? So now we can understand what's happening here. When we look at the runtime of LSD radix sort, the runtime of LSD radix sort is equal to W times the runtime of our subroutine. Okay, so a subroutine is the algorithm we use to sort all of these strings on one digit. In this case, our subroutine is quicksort, so our runtime becomes W times, or our subroutine is counting sort. So the runtime of counting sort is N plus R, right? Where R is the size of our radix, right? In this case, our radix is of size N squared. So our runtime is W of N plus W of N squared, which is dominated by the W of N squared term. Right? And this is the runtime in both the best and worst case, because in LSD radix sort, the runtime in best and worst case is the same, right? So some intuition here for why this n squared term dominates is that when we're running counting sort, we only have 5 strings, but we have to create an array of size 26, right? Because there's 26 letters in the English alphabet. So what we can kind of notice is that when the size of the alphabet is much bigger than the total number of strings, then the act of iterating through this array and counting sort of size 26 is going to dominate the runtime with respect, or dominate over like the number of strings, right? So that's like kind of why like this term dominates intuitively. So yeah, we have theta of wn squared for best and worst case here. Okay, so for the last one, we're going to run MSD radix sort with heap sort as the subroutine. Okay, so when I run MSD radix sort, what we're doing is the same exact thing in LSD radix sort, but MSD radix sort kind of sorts the digits from most significant digit to least significant digit. So when we're looking at this example here, with help Anna meet rats, notice that we're going to start from this digit right here, and then we're going to move to the right. So in MSD radix sort, what's important here to take away is that in the best case, which is the example here, all of these digits differ, in which case the first time around, I can put them in different partitions and we're done, right? So in the best case, we actually only need to call our subroutine once. So our best case here is that we call in the worst case, all of the strings keep going in the same partition, right? It's possible that the strings only differ in their last digit. Like we can have beat, bean, bear, beak, right? And all of them only differ in their last digit here. So in this case, which is kind of our worst case behavior, we have to call our subroutine W times. Well, so now that with this in mind, the next question is that how long does heap sort take when all the elements are, how long does heap sort take, right? So in the best case, if we only call our subroutine once, it means that all the elements are distinct, right? Because if we only call our subroutine once, it means that we're kind of looking at this example here. So in that manner, if I only have to call it once, then our best case is going to be just kidding. It is going to be n log n, right? Because we run heap sort once, the runtime of heap sort when all the elements are distinct is n log n, right? So now when we think about our worst case behavior is that we have to call our subroutine w times, right? So when we think about the worst case runtime of heap sort is n log n, and if we have to call a subroutine w times, our runtime is going to be w of n log n, right? So we can kind of put both of the answers here. It's going to be n log n, where are you? And the worst case is w of n log n. Okay, so that's all for this problem. I hope you all enjoyed this video walkthrough, and I'll see you all in the next one.